So we now talk about Laguerre polynomials as we continue with the special functions playlist, polynomials. So we'll look at the following topics. We look at the Laguerre differential equation. As we know already, these polynomials, these special polynomials always arrive from certain kinds of differential equations. So the Laguerre polynomials arise from the Laguerre differential equation. Then we have the Rodrigues formula from that can help us derive Laguerre polynomials. We have the generating function also, and of course, recurrence relation. So we've seen this pattern of Rodrigues formula, generating function, and recurrence relations, generating these polynomials from time, these different polynomials, like we've seen Legendre, Laguerre, Hermite in the last video, and so on and so forth. Then we also have orthogonality, which is really important, and we have the generalized Laguerre polynomials and hydrogen atom applications and some Python implementations. So let's take the introduction. Laguerre polynomials are classified. They are classified. Uh, Orthogonal polynomials that arise in quantum mechanics, mathematical physics, numerical analysis, and of course, differential equations. They are especially important in solving problems defined on 0 less than or equal to x less than infinity with exponential weight functions. Laguerre polynomials appear naturally in the solution of the hydrogen atom Schrödinger equation. So here comes the Laguerre differential equation. So the standard Laguerre differential equation is given as x, d squared y dx squared plus 1 minus x dy dx plus ny equals 0. So I think this looks a bit close to the Hermite equation, except that I think this x here, this X, there's no X here for Hermit or something like that, but there's a slight difference. But this last part looks close to Hermit somewhat. So there's just a slight difference. So where n is 0, 1, 2, and y of x is the unknown function. For integer values of n, polynomial solutions do exist. So these solutions are called Laguerre polynomials and are denoted by L sub n of x. So Laguerre polynomials are solutions to Laguerre differential equations. And if you look at the power series, like we did for Hermit also, if you assume a power series solution, y of x equals summation from k equals 0 to infinity of a sub k, x raised to power k, then if you differentiate that, you have summation from k equals 1 to infinity, that's k0 now. Differentiating shifts it to 1 instead of staying at 0. So you now have k x raised to power k minus 1. Then, and the second derivative, it goes to equals to infinity, k into k minus 1, a sub k, x raised by k minus 2. So if you substitute into this Laguerre differential equation here, so you have x y prime prime, that's d squared y dx squared plus 1 minus x y prime plus ny equals 0. So if you substitute all these things now and do all the maths, after simplifying and collecting powers of x, you obtain the recurrence relation a sub k plus 1 equals k minus n over k plus 1 squared multiplied by ak. So for integer n, the series terminates and becomes a polynomial. So for integer n, the series terminates and you get a polynomial like that. So let's look at the first few Laguerre polynomials. We have the zeroth polynomial, which is L sub 0 of x, which is 1. First polynomial, that's L sub 1 of x, which is 1 minus x. Second polynomial, L sub 2 of x, which is 1 minus 2x plus x squared over 2. And you have the third polynomial, L sub 3 of x, which is 1 minus 3x plus 3x squared over 2 minus x cubed over 6. Then you have the general formula. So the general expression for Laguerre polynomials is L sub n of x, which is summation from k equals 0 to n minus 1 raised power k, n combination k, x raised power k over k factorial. Then, of course, as usual, we have the Rodrigues formula. An important representation of Laguerre polynomials is the Rodrigues formula. So it helps us to get the Rodrigues, the Laguerre expressions, right? The Laguerre polynomials. So, just like the general formula will give us. So here you have L sub n of x equals e raised power x over n factorial, dn dxn e raised power minus x, x raised power n. So this formula is useful for proving orthogonality and for deriving recurrence relations and generating explicit forms. So we know that the first, let's say L1 of x is 1 minus x, right? So if we use this now, we can get that 1 minus x, the Rodrigues formula. So let me play with that and see. So we have L sub n of x Okay. L sub n of x generally is e raised power x over n factorial, e raised power x over n factorial, then dn dxn of e raised power minus x. I hope that's what I'm doing. Yeah, e raised power minus x, x raised power n. So, if I do want to do L equals 1, at n equals 1 rather, I have L1 of x equals e raised power x, n factorial, that's 1 factorial, then d dx, that's first derivative of e raised power minus x, x raised power 1, Um, so in short, we have x e raised power minus x because n is 1 now. So we have L1 of x equals 1 factorial is 1. So we have e raised power x times. So we need to differentiate it. That's product rule now. So hold x and differentiate e raised power minus x. That's e raised power minus x uh, multiplied by minus 1. Or better still, let's do it this way. We hold x and we multiply by uh, differentiate e raised power minus x. That's minus e raised power minus x there plus hold e raised power minus x, differentiate x, that's 1 into e raised power minus x, like that. So L1 of x now is like e raised power x multiplied by minus x, e raised power minus x, plus e raised power minus x, like that. So this cancels this. So we have minus x. Okay, no, I can't cancel like that. That's mathematical. That's mathematically incorrect. So that's e raised power x into e raised power minus x e raised power minus x. Okay, yeah, more like it. So we have e raised power x out here. E raised power minus x is common. That's 1 minus x. So then this cancels out. So we have finally have L1 of x to be equal to 1 minus x. 1 minus x. So, and that is exactly what L1 of x represents. So this now is L1 of x, 1 minus x. So we can continue with the rest, but this is how we can use the Rodrigues formula to get that. Then we come to the generating function. So Rodrigues formula, generating function, recurrence relation are things that can help you generate whatever polynomials you're looking for. So the generating function for Laguerre polynomials will be 1 over 1 minus t exponent e raised power minus xt over 1 minus t, and that is equal to summation from n equals 0 to infinity of L sub n of x t raised power n. So you just look at the t's and then collect things, you compare the coefficients of the t's, and then you get what you need to get. So this compactly represents all Laguerre polynomials. So we have the recurrence relation also. Laguerre polynomial satisfies the recurrence relation n plus 1, L sub n plus 1 of x equals 2n plus 1 minus x, L sub n of x minus n, L sub n minus 1 of x. So this relation is useful for computational purposes. So depending on what exactly you want to do, for instance, use Rodrigues for proving orthogonality, deriving recurrence, and generating explicit functions, but use recurrence for computational purposes. And then we move on to the idea of orthogonality. So Laguerre polynomials are orthogonal on the interval 0 to infinity, like closed downwards. So it means 0 is included, but infinity is not included. So with weight functions, w of x equals e raised power minus x. The orthogonality relation is then integral from 0 to infinity raised to minus x, L sub m of x, L sub multiplied by L sub n of x dx, all of that equals 0. For m not equal to 1, not equal to n. And when m and n are the same, you have everything equal to 1. So you have everything to be 1. So we have the Sturm Liouville form. The Laguerre differential equation can be written as d dx x e raised power minus x dy dx plus n e raised power minus xy equals 0. That's the Laguerre differential equation. We saw it already in a form before. So what we can also be, it can also be in this form. If you expand this, you see that it looks like exactly what we had before. So this is a Sturm Liouville problem. Therefore, eigenvalues will be real, eigenfunctions are orthogonal, and Laguerre polynomials form a complete basis. For example, one now, find L2 using the general formula. So if using the general formula, we just know L sub n of x is summation from k equals 0 to infinity to n of minus 1 raised power k, n combination k, x raised power k, k factorial. Now, L2 of x means that n is equal to 2. So if you do that, so it means you have from k equals 0 to 2. So it means you do 0. So that's minus 1, K is 0, that's minus 1 raised to power 0, that's 1. Then 0 combination K, X raised to power, okay, that'll be 0 combination 0, right? Yeah, starting from 0, that's 0, 0 combination 0. No, n is 2, right? N is 2. So we fix the 2. That's 2 combination 0. 2 combination 0 is 1, right? So we have minus 1 raised to power 0, yes. Then 1 also. Then x raised to power 0 all over 0 factorial. So everything is 1 first. Then when you go to k equals 1, so you have minus 1 raised to power 1. That's why you have this minus here. Then 2 combination 1. 2 combination 1 will be 2, I believe. And then x raised to power 1, you have x. 1 factorial is this. That's why you have this. Then when k is now 2, so you have minus 1 raised to power 2. So minus 1 raised to power 2, that's positive. That's why this is positive. Then 2 combination 2 is 1. Sure. And then you have x raised to power 2. Yeah, that's why you have x squared. Then 2 factorial. That's why you have this now. So this using the general formula like that. So, and that's for n equals 2. So we can do always do that. Then we have example 2. Verify that y equals 1 minus x. You want to verify that y equals 1 minus x satisfies the Legendre polynomial. Okay, so first derivatives, differentiate this now, you get minus 1. Second derivative, you get 0. So that means x times 0 plus 1 minus x into minus 1 plus y itself, which is 1 minus x. So you tidy up, this is 0. 1 minus x times it, that's minus 1 plus x plus 1 minus x. If you tidy all of that up, you get 0. So, and that is verified easily. So example 3 now, you want to verify orthogonality of L naught x and L1x. L naught x is 1, L1x is 1 minus x. So you just evaluate integral from 0 to infinity of e raised to minus x, 1 minus x times 1, so dx. So you just split the integral. So you can have e raised to minus x times 1, then e raised to minus x times x like this. So you then have, using standard integrals now, e raised to minus x dx, if you integrate, you get 1. And then x e raised to minus x dx, you also get 1, like that. Then, therefore, you then subtract, you have 1 minus 1, and the answer is 0. 0. So that takes us to the idea of generalized Laguerre polynomials. Generalized Laguerre polynomials are denoted by L sub n, alpha at the top there of x, and they satisfy xy prime prime plus alpha. So now you have a modification to this. Instead of the general 1 minus x thing we have there, this will now be, you have an alpha coming into play. So you have alpha plus 1 minus x, instead of just 1 minus x, y prime plus ny equals 0, where alpha now should be greater than minus 1. These are extremely important in quantum mechanics. So we go on to hydrogen atom applications. So for hydrogen atom applications here, we see that Laguerre polynomials appeared naturally in the radial Schrodinger equation for the hydrogen atom. The radial equation becomes d squared u dr squared plus 2m over h bar squared into e plus e squared, big E plus small e squared all over 4 pi epsilon naught r into minus L into L plus 1 all over r squared, all multiplied by u equals 0. So after substitution and simplification, the solutions involve generalized Laguerre polynomials. And then we have the hydrogen atom radial wave function. So the radial wave function is r sub nl into r, big R sub nl into small r, which is equal to e raised to power minus small r all over n is a naught into 2 small r all over n a naught raised to power l. And you have l n minus l minus 1, 2l plus 1, all multiplied by 12 over n a naught, where a naught is the Bohr radius, n is the principal quantum number, and l is the orbital quantum number. Then you have the ground state. So for the hydrogen ground state, n is 1, L is 0, then L01 of x is 1. Therefore, R sub 10, big R sub 10 of small r is directly proportional to e raised to minus r over a naught. This gives the exponential decay of the hydrogen ground state wave function. Then you have the orbital example. For n is 2, L is 0. The generalized Laguerre polynomial becomes L11 of x equals 2 minus x. Hence, r sub 20 of r is directly proportional to 2 minus r over a naught e raised to minus r over 2 a naught. So this wave function contains one radial node. So, and then we move on to some Python implementations now. So first of all, we import the necessary things. So here we need to evaluate Laguerre from SciPy the special, and then we have the general GEN Laguerre from the same SciPy special, and then SPI from SciPy integrate. Then we have is from 0 to 20, and then for n in range 5, we have y eval Laguerre n comma x, and then we plot. So plot all of that, and we see something like this. So blue is L naught of x, that's somewhere on the line. And then you have L1 of x, which is the orange one, L1 of x, which is also still around the line. Then, of course, you can see the gap is wide, so it may be useful to see the log. L2 of x is green. Then, of course, L3 of x is the red one, and L4 of x is this other one. So it may be useful to help to get the y scale in log form, so we can see some details that may not naturally be clear. So yeah, so you can see some things going on around all these places like this. So we want to do that sometimes. So we want to see what's going on when everything is close together like this. Then orthogonality verification using Python, of course. So if you define the integrand, orthogonality is about e raised by minus x, then you have ln of x, ln of x, and all that. So here we take m to be 2, n to be 3, and if you do all that, you get this is minus 6.9 times 10 raised by minus 17. That's as good as 0. But if they are the same, right, you expect the answer to be 1. So if you run this, the answer is 1. So if this is 2, you get something close to 0. Then if you make this 3 also, you get 1. You get 1 like that. Then hydrogen 2s wave function plots. So we have r, that's 2 minus r exponent minus r over 2, and then you plot that. This is what that looks like. You have this small r here and big R on this other side. So hydrogen 2s radial wave function is something like this. So it comes up from, goes below 0, and then stabilizes around 0 like that. Then you have the physical interpretation. Laguerre polynomials describe oscillatory radial behavior in quantum systems. Oscillatory radial behavior in quantum systems. In the hydrogen atom, zeros correspond to radial nodes. Orthogonality ensures independent quantum states, and exponential weighting ensures normalization. So the number of radial nodes is n minus L minus 1. Then you have completeness expansion. So a sufficiently smooth function can be expanded as f of x equals summation from n equals 0 to infinity of Cn L sub n of x, where the coefficients are C sub n, integral from 0 to infinity raised to minus x f of x L sub n of x dx. This is analogous to Fourier series expansions. Then you have the Gauss-Laguerre quadrature. So the Gauss-Laguerre quadrature evaluates integrals of the form integral from 0 to infinity e raised to minus x f of x dx using the approximation summation from I equals 1 to n of w sub I f of x sub I, where x sub I are roots of L sub n of x, w sub I are weights. This method is widely used in computational physics and engineering. In summary, we see that we have some important equations. The Laguerre differential equation is xy prime prime plus 1 minus xy prime plus ny equals 0. Then we have the Rodrigues formula, which is L sub n of x equals e raised by x over n factorial, dn dx and e raised by minus x power n. And then orthogonality relation integral from 0 to infinity raised by minus x, L sub m of x, L sub n of x dx equals 0. For m not equal to n. And then we have the generalized Laguerre equation. Instead of just the normal 1 minus x, now we now have alpha plus 1 minus x, where alpha must be greater than minus 1, by the way. Because if alpha is minus 1, this cancels and we just have minus xy prime. So we then have Laguerre polynomials being fundamental in quantum mechanics, spectral theory, and orthogonal polynomial theory, as well as numerical integration. So we have some practice problems. First of all, we want to show that L4x is 1 minus 4x plus 3x squared minus 2x cubed over 3 plus x raised to 4 over 2, 24. Using the general formula for Laguerre, yeah, then you have problem 2 here. Let me see how many we can fit in at the same time. Okay, let's do it. We can do 3, right? This 1, 2, 3, 4 to say 7. Should be able to show 4 to 7. So we have 4 to 7, and then we have 8 to 11. 8 to 11 here, then 12 to 15, then 16 to 18, and then all of that all the way to 18 to 20 now. So let's see. I'll be doing 2 as usual. I'll be solving 2 as usual. So the 2 will include problem 7 and problem 17. So see problem 7. Use the recurrence relation this to compute L3 of x from L1 of x and L2 of x. And then 17, for the hydrogen atom, determine the number of radial nodes for n equals 4, L equals 1, using radial nodes to be n minus L minus 1. Okay, that looks pretty straight to the point. So let's go on and deal with this. So problem 7 it says to use the recurrence relation, n plus 1, L sub L plus 1, L sub n plus 1 of x equals 2n plus 1, 2n plus 1 minus x, L sub n of x minus n L n minus 1 of x. We want to use that to compute L3 of x, to compute L3 of x from L1 of x and L2 of x. So step 1, so we use L1 of x, which we already know to be 1 minus x, and we use L2 of x, which we already know to be 1 minus 2x plus x squared over 2. So if you don't know this, we have to derive them, right? And then that means we want L3 of x. So following this expression now, since we want L3 of x, so we need to set n to be 2. So for L3 of x, we say 3 is n plus 1. That implies that 3 minus 1 is equal to n. That means n is equal to 2. So we set n to be 2. So since n is 2, then we can use the formula now. So I'll take the pain to write the formula again. It's n plus 1, L sub n plus 1 of x equals 2n plus 1 minus x, L sub n of x minus n L sub n minus 1 of x. So now that n is 2, so this will be 2 plus 1, 3, L3 of x equals 2n plus 1. That's 2 times 2, 4, plus 1, that's 5, minus x. This is 5 minus x, L2 of x minus 2, 2 minus 1 is 1 of x. So we just need to put everything together. So we have 3L3 of x equals 5 minus x. So L2 of x is 1 minus 2x plus x squared over 2. So 1 minus 2x plus half x squared minus 2. L1 of x is 1 minus x. 1 minus x. Hope that's correct. Yeah, 1 minus x. So we just tidied this up. So we have 3L3 of x to be, okay, I guess the expansion can start already. 5 times 1 is 5. 5 times minus 2x, that's minus 10x. 5 times 1 over 2x squared, that's 5 over 2x squared. Then we have minus x times 1, that's minus x times minus 2x, that's plus 2x squared, minus x times half x squared, that's plus half, that's minus rather, that's minus half x cubed. And on the other hand, we have minus 2 times minus 1. Minus 2 times minus 1 is minus 2. So I put it along with the constant. Then minus 2 times plus x, that's plus 2x. That's plus 2x. So with this now, I just arranged it in a way where for us to be able to tidy things up easily. So we have 3 L3 of x to be 5 minus 2. 5 minus 2, that is 5 minus 2, that's 3. Then 10 minus 10 minus x, that's minus 11x. Minus 11x plus 2x, that's minus 9x. That's minus 9x. Then 5 over 2 plus 2, that'll be 5 over 2 is 4 over 2. That's 9, that's plus 9 over 2 x squared. Then minus 1 over 2 x cubed. Then now we have this 3 here. So that means we have L3 of x to be. So we just multiply 3 by, we divide 3 by 3. That's 3 minus 9 over 9x plus 9 over 2x squared. Well, I mean, I think it's easier to multiply through by 1 over 3. So 1 over 3 into 3 minus 9x plus 9 over 2x squared minus 1 over 2x cubed. So that L sub 3 of x would now be 1 over 3 times 3, that's 1. Minus 9 over 3, that's minus 3x. Then 3 here, 1, 3 here, 3 and 9, 3, that's 3 over 2x squared. Then on the other one, 1 times 1 is 1. 3 times 2 is 6. So that's minus 1 over 6x cubed. And that is what all of that is about. 1 minus 3x plus 3 over 2x squared minus 1 over 6x cubed. So that's problem 7. Then we go for problem 17. Problem 17. So for problem 17 now, see what we get. It says for the hydrogen atom, determine the number of radial nodes for n equals 4, L equals 1 using radial nodes equals n minus special L minus 1. So let's go for that. First step, the solution will be to substitute the given quantum numbers. N equals 4, L equals 1 into the formula, radial nodes equals n minus L minus 1. So then it means that radial nodes will just be 4 minus L is 1, right? And n is 4, L is 1, minus 1 again. And that is simply 2. So we have 2 radial nodes. So we can say that, so the hydrogen state with n equals 4, L equals 1 has 2 radial nodes. And what's the implication of that? That simply means that radial nodes, radial nodes are values, they are values of R where the radial wave function becomes becomes zero. These nodes, these nodes correspond to regions where the probability density of finding the electron vanishes. Yeah, and with that, we come to the end of this video again about uh Laguerre polynomials. So I'll flash the questions once again, and that'll be all for now. So problem 1 to 3 here. 1 to 3. Then we have 4 to 4 to 6. 4 to 6. Then 7 to 10. Yeah, 7 to 9. 10 to 13. 14 to 16. Well, 14 to 16. Then 17 to 19. And then we show 20. All right, let me know how helpful this is for you. And if there's something else you'd like me to do, let me know. Ultimately, don't forget to comment, like, and share. Um, if you have not subscribed already, of course, you want to do that, and also hit the notification bell so you can always get alerted each time a new video is released. You can become a member of the channel, which gives you some special privileges. And don't forget to comment, like, share, so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.